So yeah, thanks, Marius, for the introduction. Also, thanks for inviting me to give this talk. So yeah, as Marius mentioned, I'm Jim, and I have written my master thesis about querying state. So the title of my master thesis is As Query, Opening the Black Box of Internal Stream Process State. And actually, this has also been now developed into a paper, which is kind of what I'm going to present now. So yeah, let's get started. So first, let's start off with stream processing 101. So basically, to give you a bit of background information on what stateful stream processing means. So let's start with stateful stream operators. So a stateful stream operator is basically a stream operator which takes in a number of data items. For example, in this case, it takes in data items from a source and it sends out data items to a sink. And let's say we have here an example operator, which is the averaging operator. So what this does is it simply takes in an item, calculates the average of all the items it has seen so far, and will output it to the sink. So in this example, we first have 10. Of course, the average of 10 is 10. Average of 10 and 30 is 20. And the average of all items is 15. And the reason that this is a stateful operator is that it has to keep track of state inside itself. So for example, here for the average operator, we need to keep track of both the count and the total in order to calculate the average, of course. And this is just a very simple example, of course, of what a stateful stream operator can do. And the actual problem then is to be able to query this internal state in a stateful stream operator. And before I go further, I would first like to give a bit more background information. And that is more about stream processing in general. So how these systems work and how we scale them. So you can think of streaming systems as directed acyclic graphs. And these graphs then represent the streaming structure. So in this example here on the left or on the right, we have a source, which I'm accidentally clicking, which has a source, sends it to a stateful operator, another one, and to a sink. And this is just a very simple example again to illustrate. But what is special about this is that we can actually horizontally scale this system across multiple nodes. So for example, this entire streaming graph can be distributed and basically copied to multiple nodes where the difference is in the source. So each source basically is responsible for a certain set of keys they have to process. And using this mechanism, we can horizontally scale such a stream processing system. And this will be also mentioned later on in the presentation. So that's why I wanted to highlight this. And the final piece of background information is checkpointing. So checkpointing can be explained in basically three simple steps. So first we have, let me explain first what checkpointing is used for. So it's used for exactly once processing. And it's basically can be subdivided into three separate steps. So first we have here a stream operator. You could think of the averaging operator, for example. But in this case, we have multiple input streams and one output stream. And what checkpointing means is that next to these circles, which are the data items, we also have these rectangles. So the 9 in this case. And this is actually a marker. And this marker has to go to the stream operator. And in step 2, we can see here that the markers have to be exactly at the stream operator. So without any data items between it and the operator itself. And when this happens, the stream operator knows that it has to take a snapshot of itself, of its state. And this is done in between step 2 and 3. And when it's done, it will actually forward this marker on towards the next operator in the directed acyclic graph. And this is basically used to have exactly once processing guarantee. I'm not going to explain exactly how this is ensured, but basically you are making a snapshot every time. And in case something fails, you can just restore from that snapshot and restore missed streams from your source, streaming items from your source. So this is also important to know because it will be used later on in the presentation. So that was basically the background information. So now let's move on to why we actually want to be able to query state, because of course you don't want to do something if there's no use case for it. So I have here highlighted a couple of important use cases. And I'll first start with the first two because they're quite intertwined. So substituting caching and static views and eliminating slow databases. And in order to illustrate these 2 points, I have here on the bottom 2 diagrams. So on the left here, we have what you could call like a traditional system where you just have some events that are sent to a database and which are served to users through a caching system to improve performance. And on the right here, we have a more modern system which directly uses the stream, processes it in a stateful transformer, and is able to serve this state directly from the stream processing system itself. So without the need for a database or a cache. So as you can see here, we have this complete middle layer of databases and caches completely replaced by a single stream processing system. So this way you are actually eliminating a lot of complexity and caching logic by just having a single system that is able to serve your source of truth, basically. And I'd also like to highlight the third and fourth point, so debugging. So for those of you who are familiar with stream processing, it can be quite hard to debug actual systems that are inside production environments because you cannot just hit a breakpoint somewhere. So if you are able to actually query the internal state of such a stateful stream operator, it's much easier to see what is going on inside and to actually troubleshoot problems that you might have. And last but not least, also auditing and compliance. So I guess a lot of you here are also from Europe, so we all know about local regulations here. And one example of this is, for example, if you're processing the private user information from a certain user, for example, the location of that user in a stateful stream, then you must be able to actually provide the user with that data because by law, of course, if a user asks for it, you have to be able to provide it. So there's several pretty important use cases for querying state in stateful stream processors. All right, so now that you know why we want to do it, how can we actually tackle this problem? So how are we going to solve it? So to do this, I have devised some research questions for my thesis. So these are, so basically the grand question is, of course, how can state be exposed from stateful stream operators? And in order to answer that, I have 3 sub-questions. So how can it minimally impact the stream processing performance? How could it work in a distributed setting? Because of course, as I mentioned before, we want to horizontally scale the system. And finally, what consistency guarantees are achievable when querying the state? So now that we know what it is we want to do, let's talk about how we solved it. So of course, since this is a seminar on system design, this slide cannot miss with the actual system design. So let me now explain the high-level architecture of what we developed, which is called sQuery, short for state query. And I will explain this by first going from top to bottom, basically. So and first, what I actually should mention is that sQuery is actually an architecture, so not necessarily a implementation, but more of a high-level architecture that can be applied to any actual stream processing system that uses checkpoints. So let's start here at the top of the stream processor level. So the stream processor is basically your system with the stream operators. And these stream operators are distributed across different nodes. So you can have any amount of nodes, of course, to horizontally scale your system. And these operators are distributed across these nodes. And as I mentioned before, there are checkpoints going from operator to operator, etc., which indicate that they have to snapshot their state. And when this happens, so for example, when this 9 comes into this operator knows that it has to snapshot its own state, and it will do this by storing it into the state store, which is the bottom part. So it will do this in the snapshot state store. And as you can see here, there are 2 IDs here, so it will keep track of the latest 2 snapshots, and it will store it in this state store. And in addition, we also have the live state here, and this is basically a one-to-one copy of the actual internal state. So this doesn't have to do with snapshots anymore. This is just really a one-to-one copy. So whenever the internal state changes, the live state changes as well. And finally, what I couldn't fit in this slide, but there's also incremental snapshots. So these are basically snapshots that are also saved to the state store, but instead of snapshotting the entire state in operator A, for example, it will only snapshot the actual changed state. So this is actually an optimization. However, it's not optimal in all cases, which I will also show later. And finally, what I also would like to highlight is that, of course, without being able to query state, it's useless. So there has to be a query system. So in SQuery, so yeah, this is more the implementation part. We provide an SQL interface, also a direct object interface, which is basically a very low level Java API. And the SQL interface is, as the name suggests, just a SQL interface with a SQL-like dialect. And finally, what I want to mention in this slide is the use of a latest snapshot ID. And this is actually a very important part of SQuery, because this is the actual thing that can ensure high isolation levels when querying the actual state. But I will explain that in a later slide. So now about the implementation. So as I said, SQuery is more of a architecture. So in order to implement it, I implemented it on top of Hazelcast Jet, which is a stream processing platform, which is capable of processing very many events per second. So that's why I initially chose it. But it also has IMDG, which is an in-memory data grid. And this is very useful to be able to store the live and snapshot states inside memory, because of course storing to disk is quite slow. So in memory is much faster, but of course has some downsides because it's volatile. Yeah, that's what I'll talk about later as well. And of course, some more boring stuff. So some configuration system and a custom query utility was written. So you don't need to actually first get the snapshot ID manually by hand and then putting it inside your query. So this is all done automatically. But what is important is the distributed atomic integer, which I mentioned from the last slide, is basically this thing over here, the latest snapshot ID. This is implemented as a distributed atomic integer using an implementation based on Raft. So we are always sure that this latest snapshot ID is consistent across all nodes in the cluster. All right, so now let's take a look at how we actually can query the state. So I have here an example of the average operator again, which we have seen before. So we have here the count and total, and we want to query this. So there's three ways we can query this: either the live state, snapshot state, or incremental snapshot state. And in order to query this with live state, we just have a very simple query because there's no need to keep track of snapshots or anything. So you just query what you want and from the key that you want. And by the way, the key here is the key I mentioned all the way in the beginning of the keyed source, because this key is actually used to partition the stream across multiple nodes in the cluster. Yeah, so in this example, it doesn't have very much meaning, but in a real world use case, you could think of this as like a user ID, for example. And the second way to query this is using snapshots. So if you want to query this state as a snapshot, you just go to the snapshot state store and query it using the latest snapshot ID. So in this case, as you can see here, the latest snapshot ID is 9, which is what you would get from this distributed atomic integer. And you would insert that into your query and then query the actual value and get your result. Similar to what you did at a live state. And the more intricate one is the incremental snapshot, because in this case, even though the latest snapshot ID could be 9 globally, your state might not have changed even since, like, for example, snapshot ID 5. So from 5 all the way to 9, if the state doesn't change, it will also not change in the incremental snapshot state store. So in this case, in order to query it, you would actually have to do some join and group by this key and select the highest one, but also make sure that you're not querying higher than the latest snapshot ID, because in that case, you could actually get a state that is not completely written yet. So for isolation level purposes. So this is basically how to query the state, very shortly, basically. And an actual proper use case of this is, of course, different from just querying some counters. So we actually work together with a company called Delivery Hero. And this is a company doing like quick commerce. So you probably know, especially in the Netherlands, like Gorillas and other competitors there, and delivering like within 50 minutes. So for them, being able to have real-time statistics is very important. So actually using sQuery, this becomes actually a matter of writing a single SQL query and being able to real-time view your data without any convoluted caching logic, as I mentioned before. So just this simple, well, it's not very simple, but still using a single SQL query, you can see and know for sure that this data that you're querying is, for example, at most half a second old, for example. And as you can see here, you can see the results on the right, which allows you to basically have real-time insight into your streams. And this is very useful compared to having a custom system with a database and caching layer and having to manually configure how up-to-date your caching needs to be. And that can cause a lot of problems with your database, causing high load. Whereas in this case, you can just query it from the stream processor, where the load is distributed across the nodes, so horizontally. Right, so now let's talk about the isolation levels. So there is actually different isolation levels in sQuery. So the live state has the read uncommitted isolation level. And this is simply due to the fact that there are dirty reads possible. So for example, if you're querying live state while there is a crash, it will actually restore the state from the snapshot and get a different state. And therefore you are committing you are querying a dirty value that's actually already out of date. Whereas for the snapshot state, by design, of course, you are querying a snapshot. So of course, since the snapshot never changes, you inherently don't have this problem. So you automatically, by deduction, get the serialized isolation level. And I should mention that you, of course, only get this when you use the latest snapshot ID, because if you don't use that, you might get a partial snapshot state. For example, if snapshot 10 is currently being written, but it's only done for half of the state, you might have like an inconsistent view of the state. So it's always important to use the latest snapshot ID. All right, so now let's talk about the evaluation of sQuery, because of course we want to know if it performs according to expectations. So in order to measure this, one of the experiments we did was measuring the overhead of sQuery. And to measure this, we simply compared the performance of sQuery compared to the original Hazelcast jet, which is what sQuery is built on top of. And as you can see here on the right, by the way, let me first explain this graph. So of course, on the y-axis, we have the latency. And on the x-axis, we have an inverted logarithmic scale of percentiles of this latency. And as you can see here, on the right, we have a legend indicating how many million events per second we are running. So for example, here, the top one is sQuery running 1 million events per second, and 5 million, 9 million, and so forth. And in this case, you can actually see that the difference is there. So of course, this makes sense because you're adding functionality on top of something else. So there will be overhead. However, it is noticeable that it's only a couple milliseconds in this case. So I think the largest difference here from this graph is like 7 or 8 milliseconds. So for very latency sensitive applications, you might not want this. However, for I think majority of applications, this is a very acceptable trade-off compared to the functionality that you get in return.
So Jim, just for the avoidance of doubt, the latency that you're mentioning here is the latency of your stream, your standing stream queries, like average.
Okay, so these are actually, yeah, good that you say it, because this is the latency of the stream from of the data items that go from the source to the sink. So not the actual queries themselves yet. That will actually, I think in a later slide, I will show that.
So what kind of queries were those?
So actually, let me see if that's the next slide. Oh, that's all right. Yeah, so let's talk about this slide. So these queries that I did were different types of queries. So in this example, I did the direct object interface queries, which are basically the very low level Java API queries. So without SQL. So of course, these are much faster because they don't have to do any optimization or like any SQL processing behind the scenes. They can just directly grab the Java objects. And other queries I did were actual SQL queries, but I can also show that I think they are not currently in this slide deck, but I do have it, I think a hidden slide, so I can show it later.
But now I'm confused. So the queries you are now referring to, these are the state queries.
Yeah, they're all state queries. Yes, that's for sure.
Okay, but on the previous slide you showed latencies. They were also for state queries.
No, these are for actual stream processing itself. So
yeah, exactly.
Yeah.
So, but what was your stream actually computing? Was my question.
Okay. So there is this example, which is the nextmark query. So I think this is a benchmark that is not really computing. I think, what was it computing? It was computing some kind of stateful operation with quite heavy mathematical calculations, but not like not the use case I showed from before. So no like user data or anything. So basically a real benchmark in order to compare these results.
But you're qualifying your stream workload as doing heavy mathematical calculations.
Yeah, stateful calculations. Yes.
Yeah. Okay.
So yes, that was in this experiment, and in the next experiment, I'd like to show another component of performance, which is the actual snapshot latency. So this is again a different kind of latency. So this latency is the time it takes to make a snapshot from the state of a stream operator. And as you can see here, I have measured this for different settings. So I have measured this for taking a full snapshot every time of the whole state. And I've also measured this for incremental snapshots. And in the case of incremental snapshots, I've also adjusted the delta ratio. So this delta ratio is actually standing for the amount of state that changes between each snapshot. So for example, 1% means that only 1% of the state changes, 10%, 10%, and 100% means all the state changes between each snapshot. And as you can see here, this actually shows that basically the crossover point between doing incremental snapshots and full snapshot is at 10% roughly. So basically what that means is that once you go above a stream that changes more than 10% every snapshot iteration, you're better off just doing a full snapshot because it has less overhead. However, if you're below the 10%, it's better to do an incremental snapshot. So of course, this will depend on the actual stateful stream that you're doing. So it's not a general rule, but this is basically a trade-off that you can have to make. And now back to this slide about queries. So of course, what we also want to know is how performant our query system is. So in order to measure this, we measure both the performance of sQuery and another system called Teaspoon. And this system is what we could find in existing literature that's most closely matched what sQuery was trying to achieve. So it does query the state of a stateful stream processor. However, Teaspoon only supports like what I mentioned before, the very low level Java API key value lookups. So you technically it's a query, but it's not really a query in the sense that you can do a bunch of joins, for example. But in order to do this comparison, we implemented this API in sQuery as well. And as we can see, the results are pretty similar. So sQuery outperforms it when only selecting one key in a query or in the get statement. And in the other scenarios, it's roughly similar. And as you can see, it follows some kind of roughly a power line distribution. So it's good to see that at least they are performing similarly, and it's not underperforming compared to Teaspoon. And the next experiment, which is also quite important, is that your system is still scalable. So in order to test this, we measured the maximum throughput of sQuery, and this throughput is then plotted against the degrees of parallelism in your cluster. So, and the degrees of parallelism are just the amount of cores you have. So in this case, we did, I believe it was 3, 5, and 7 nodes of 16 cores. And this is showing a pretty linear relationship. So you could say that this is linearly scalable. But what is also interesting to note here is that we also use different snapshot intervals. And what you can also see here is then that the maximum throughput for a lower snapshot interval will get lower because your overhead of doing snapshot still impacts your maximum throughput somewhat. So this is, again, a trade-off that you have to make of the liveliness of your snapshots versus the maximum throughput that you want to achieve your system. And finally, what I would like to mention are like key findings or maybe takeaways that I'd like you to remember from this presentation is that queryable state is actually very useful in many scenarios, and it's actually not been explored that much yet. So I hope this presentation will contribute to that. And more generally, so it is possible actually to query state while minimally impacting the streaming performance, and also possible to actually safely query this with the serialized isolation level. And also more about the experiment. So the incremental snapshots are quite useful to do when state doesn't mutate often. However, the opposite, of course, when it does mutate often, you're just better off using full snapshots, depending on your use case. And there are many trade-offs that you have to consider. So for example, snapshot interval compared to latency and throughput. And I hope that, yeah, that was basically it, I think, for this presentation. So if you have any questions, yeah, feel free to ask.